So in the last video, I said that Planck made an assumption that light comes in pieces rather than a continuous wave. But I said that he didn't realize that his assumption was actually reality. We have a new phenomenon now called the photoelectric effect, okay? And it demonstrated inconsistency with the wave model of light. It turns out the answer to that inconsistency is Planck's particle ideas, his pieces of light, thinking of light as being a particle as well as a wave. And it took Einstein to unravel all that. So first of all, what is the photoelectric effect? Well, what it is when you've got a piece of metal and you have some light that shines on the metal. Draw a dodgy light bulb, right? Depending on the right conditions, sometimes electrons come off from the metal. Yep, light shines on it, gives the electrons energy, the electrons jump off. Okay, now why does this demonstrate inconsistency with the wave model of light? Well, this is why. The electrons come off with a certain velocity, right? Certain velocity, which means a certain kinetic energy, right? They're getting that energy from the light. So you would imagine if you increase the intensity of the light, i.e. if you have more energy in light from its intensity, then these electrons, when they come off, they should come off with a higher velocity, right? This was the proposal. The proposal was more intensity of light means a higher velocity of the electrons that shoot off when the light hits them. Intensity has nothing to do with how fast the electrons travel when they fly off. That was the inconsistency of the wave model of light. What's more, you can increase the velocity of the electrons coming off, and it's got nothing to do with increasing the intensity of light. It has everything to do with the wavelength of light or the frequency. So if you use a different light bulb, a light bulb that emits blue light rather than this yellow light, it's actually going to emit electrons at a higher velocity, a much larger velocity than the yellow light. So this one, nope, no high velocity, even though we had high intensity. Here we have really low intensity, but we are getting a high velocity nonetheless. So they could not understand this. As a wave, this has more energy than this, so therefore the electron should have more energy as well. Why is it that the lower energy beam of light results in higher energy particles? The answer is that this beam of light is actually made itself out of particles. So instead of thinking of it as a line or a continuous wave, we think of it as packets of waves. Right? And just so happens that blue light packets of waves are each bigger than yellow light packets of waves, right? So we get much smaller yellow light packets. However, the yellow light that I've drawn here is more intense. That just means we have more of the packets, but each individual packet is still a lot smaller than the blue ones. So we have an army of many, many, many tiny yellow packets of energy, and then we have here a small band of really strong blue light waves called photons. Okay, and one blue photon getting absorbed by this electron gives it this high velocity, but one little yellow photon getting absorbed by this electron gives it a smaller velocity because that little yellow photon does not have as much energy. This comes from the equation we looked at in the last one, which is the energy of a piece of light is equal to Planck's constant times the frequency of light. Okay, and the blue light has a higher frequency than the yellow light has a smaller frequency. So that's where that extra energy comes from. Now, this yellow light can be more intense because it's got more particles, and what that will do is it will excite many more electrons than the blue light did. But each of those electrons is going to have a lower velocity because each electron can only absorb one photon of light at a time, can only jump off with the amount of energy that single photon gives it. So if you want to have an electron with the highest amount of energy, you have the highest frequency. That's going to be gamma rays or X-rays. Something with a really low frequency, like microwave or infrared, probably can't even make an electron jump off a screen at all. In fact, it was originally discovered that UV light was able to knock electrons off a sheet of metal. That was the first observation of the photoelectric effect. So, two big pieces of evidence to say that, hey, maybe light doesn't behave as a wave. One, black body radiation. When you assume that light can behave as a particle, comes in pieces, then suddenly the maths for the black body radiation curve start to work out. Also, the photoelectric effect. If you know that light is a particle, then the photoelectric effect makes sense. Bigger particles mean more energy for the electrons. However, if you think of it just as a wave, then it doesn't make sense, because then the wave with the higher energy doesn't necessarily have the higher energy electrons coming off. Okay, next dot point here, we're going to analyze the photoelectric effect using this equation as it occurs in metallic, here's our metal, elements by applying the law of conservation of energy and the photon model of light. So we know that this is the big part of the photon model of light. A photon is a piece of light, and its energy depends on its frequency and Planck's constant. And you can see that energy appears right here, HF. HF is the energy of a photon. So if we grab this equation, copy that, let's get rid of all this, boom. Let's analyze what's going on here. Okay, K is the kinetic energy of the electrons. So we have our sheet of metal. We have an electron that's come off the sheet of metal, and it's got a certain amount of kinetic energy. Okay, now where does that kinetic energy come from? It comes from the photon of light it absorbed, right? It originally absorbed a photon of light. The energy from the photon of light is now gone into the electron. What energy did this have? It had Planck's constant times frequency, this energy right here. So the kinetic energy is the electron. Where does it get it from? It gets some of that energy from the energy of the photon. Now, phi here is the work function. The work function is how much work, how much energy you need to get the electron out of the metal in the first place. The metal is held in there, kind of like a potential energy holding it in, and you need to overcome that amount of energy to put that in order to get the electron out. Okay, so you need to put in, so you have the energy of your photon, you have to minus how much energy it takes to get the electron off the metal, and then once you've done that, that's how much kinetic energy your electron can have. This all only makes sense using the particle model of light. If you've got just the wave model of light, what Maxwell said, then this doesn't make sense. Does this mean Maxwell was wrong? No. Light does behave as a wave in some circumstances. However, it also behaves as a particle in other circumstances. In reality, it's neither. It's got a wave-particle duality. It's sort of got bits of both at the same time.